The next group, of the next two speakers, George Clark and Bill Crosshar, are two of the very productive group that Fred described in his talk, the cosmic ray group. The remarkable thing about that group was to see with what insight it moved from one related series of experiments to another. Again, I won't go through what Fred described so well, but moving from looking at the primary radiation to using the cosmic rays to try to look for the origin of cosmic rays, and then moving to essentially a succession of experiments that look at cosmological questions. And it has been an inspiration to watch. George, who speaks first, specialized particularly in X-ray sources and the measurements of X-ray sources, has worked, I think, flew the balloon experiment that saw the X-rays from the Crab Nebula, and then a sequence of experiments on various satellites and observatories. So let me turn to George.
I was a Johnny-come-lately when I joined the MIT Cosmic Ray Group. It was a flourishing enterprise in the Laboratory for Nuclear Science and Engineering when I joined as a graduate student in 1950. I was put to work experimenting with the new scintillation counters, and when I finished my degree, Professor Rossi invited me on a journey of exploration that would be guided by his unerring sense of scientific opportunity. That sense and the gentle, firm hand with which he steered the Cosmic Ray Group into the future had already established MIT as a center for the exploration of cosmic physics and high-energy particle physics. Now, this first slide is the jacket cover of his recent autobiography. It's a bit dim, but I think you can see in that gray the young Rossi pointing into that future from a perch on top of the mountain where he discovered the radioactive decay of the muon in 1939. And just beside him is his energetic wife, Nora, who's helped many of Bruno's young associates over life's rough spots. Professor Rossi had laid the foundations in the 1930s for rapid progress in cosmic ray research after the war. In 1929, he was a 24-year-old assistant in the physics laboratory in the University of Florence, and he was looking around for something new and interesting to do in physics. And then he read the paper of Botha and Kohl-Herster about a coincidence experiment on the penetrating power of cosmic rays. Rossi tells how he was galvanized by a desire to improve on that experiment and to begin his own exploration of what was a virgin field of physics. Within a few weeks, he had invented the first coincidence circuit. It was a device that employed the new technology of triode vacuum tubes, and it was soon known throughout the nuclear physics world as the Rossi coincidence circuit. That invention initiated the application of electronic methods in cosmic ray and particle physics, and it was the precursor of the AND logic circuits of modern electronic computers. When he began his work, in 1930, it was generally believed that the primary cosmic rays were gamma rays. And the famous Robert Millikan held that they were gamma rays born in what he called the birth cries of the atoms synthesized by some mysterious process in interstellar space. The binding energy of the most massive nucleus is some 500 million electron volts, put a rather severe limit on the possible energy of the gamma rays. And then, with Geiger tubes and this new coincidence circuit, Rossi carried out a series of momentous experiments that demolished those ideas. Here is a very brief summary of those remarkable experiments. First, he demonstrated that the existence of penetrating charged particles with more than 1 billion electron volts exist in cosmic rays, and they're capable of traversing a meter of lead, the particles which were subsequently identified as muons. In this experiment, he had the 3 Geiger tubes connected in coincidence and a total of 1 meter of lead through which they could penetrate. Secondly, he discovered what came to be known as the Rossi transition effect, which illuminated the production of multiplicative showers and stimulated development of the quantum theory of electron-photon cascades. In this case, the 3 Geiger tubes were placed in a triangular array so that they could only be triggered by more than one particle. And third, he measured the east-west difference in the cosmic ray intensity, which he had predicted in 1930 in a theoretical analysis of the different effect of the Earth's magnetic field on the trajectories of positive and negative particles. The experiment is illustrated in the bottom, where the Geiger tube telescope is pointed to the east and then to the west. Actually, others using this coincidence method beat him to the actual discovery by a few months in 1934, but in any case, the results proved that the primary cosmic rays are mostly positively charged particles, probably protons. And in addition, in the course of that east-west experiment, he discovered that what he characterized in his 1934 publication as very extensive showers of cosmic ray particles in the open air was a phenomenon that would occupy the MIT Cosmic Ray Group 20 years later. Professor Rossi told me recently, and perhaps with a bit of nostalgia, that those were simple experiments. Yet his results were so startling that he had trouble getting some of them published. They did not earn him the friendship of Robert Millikan, but they did indeed change the direction of cosmic ray and particle physics, and they won him a professorship at the University of Padua at an early age. In 1938, the fascists forced Rossi from his position as the director of the Institute of Physics that he'd created at Padua. He left Italy, and after a year in Copenhagen and Manchester, he and Nora came to Chicago at the invitation of Arthur Compton. Rossi had an idea about how to detect the possible radioactive decay of what were called in those days mesotrons. Those were the particles of penetrating radiation that he had measured in the early 30s and which had recently been identified by Street and Stevenson at Harvard as particles with a mass of about 200 times the mass of the electron. He built new equipment to measure the intensity of mesotrons, and he took it to Colorado, where he operated it at various altitudes on Mount Evans. He proved that mesotrons do indeed suffer radioactive decay by showing that their intensity is reduced more by passage through a given thickness of air than by passage through an equivalent thickness of graphite. The difference is due to the loss of mesotrons by radioactive decay during their time of flight through the tenuous atmosphere. And that result was the first demonstration of the instability of a subatomic particle other than the neutron, and it gave a rough value for the mean life of the order of a microsecond. In 1940, Rossi moved to Cornell, where he and Narrison measured the precise mean life of the stopped mesotrons in a classic particle decay experiment, which was the first of its kind, for which he invented the electronic device now known as a time-to-amplitude converter. And in this figure, you see the beautiful exponential decay curves of positive mesons that have been brought to rest first in lead and then in brass. Then came his work at Los Alamos, which culminated in an experiment at the Trinity test, where he measured the exponential rise of ionization in an ion chamber placed next to the detonating plutonium bomb. He used a technique that was known at Los Alamos as the Rossi sweep. It was one in which he applied a high-frequency sinusoid to the vertical deflection and in fact, he was using the fastest oscilloscope available in the country at the time. So the beam of the oscilloscope was sitting there oscillating in the vertical direction behind a mask to avoid overexposing the film. And the signal from the ion chamber was applied to the horizontal deflection. So when the bomb went off, the beam of the oscilloscope was driven to the right at an exponentially increasing speed, which could be measured directly in terms of the frequency of the vertical oscillation. The figure shows that sweep, and below, the actual photograph from the Trinity test in which the split second between the pre- and post-atomic age is frozen as a faint trace of the signal from the ion chamber before it was vaporized. And you can see just here the first couple of oscillations of the vertical oscillation as the ionization drives the beam across the face of the oscilloscope. So that was the prologue to the Rossi era at Laboratory for Nuclear Science, which Fred Epling has sketched. And as Fred said, there were 4 young physicists that came with Rossi from Los Alamos: Herbert Bridge, Matthew Sands, Robert Thompson, and Robert Williams. They were soon joined by John Tinlow and Robert Hulsizer, who'd worked at the MIT Radiation Laboratory. And though they came as PhD students, they were already experienced researchers who were quite ready to tackle the problems of cosmic rays in the kind of independent and collegial way that has been an enduring characteristic of the cosmic ray group. Rossi defined 2 research themes, both extensions of his previous cosmic ray research. The first theme was the nuclear interactions of cosmic rays and the particles generated in these interactions. And the second was the composition and properties of the primary radiation. And one should recall what was and wasn't known in 1946. From the East-West experiment, it was known that the primary radiation is mostly positively charged particles, probably protons, with energies that extend beyond 10 GeV. Unknown was the presence of heavy nuclei and electrons at the level of about 1%. And there were inklings of radio waves and solar X-rays, but the richness of the non-visible spectrum from radio to high-energy gamma rays was quite unexpected. As for the cosmic radiation in the atmosphere, it was known to consist, first of all, of a soft component of electrons and photons that are readily absorbed in a few centimeters of lead. There was a hard component of penetrating particles, the mesotrons, capable of traversing great thicknesses of lead unscathed. And there was a component capable of generating showers of penetrating particles that can be detected by arrays of Geiger tubes that are buried in a pile of lead. In particle physics, there were 5 so-called fundamental particles: protons, neutrons, electrons, neutrinos, what were called mesotrons, and 1 antiparticle, the positron. Those mesotrons, which are now called muons, were thought to be the glue of nuclear force, predicted by Yukawa. But doubts had been raised by recent experiments that showed they hardly interact at all with the nuclei that they were supposed to glue. Unknown were the pion and the zoo of particles and antiparticles made from quarks that constitute our current world of the Standard Model. Cyclotrons, could provide experimenters with protons of several tens of MeV, but machines capable of creating anything heavier than electrons were still several years in the future. Now, certainly many groups and individuals around the world contributed to the remarkable progress in the next 15 years. But in this short time, I obviously can't do justice to so complex a history, and so with apologies, I'll concentrate on the contributions from the Rossi group. First question addressed was, what is the cause of those penetrating showers? And in particular, are they generated by mesotrons? John Tinlow put that idea to rest by measuring the rate of penetrating showers as a function of altitude. He took his detectors up and down Mount Evans and even to higher altitudes in a B-29. And he found that the rate of penetrating shower production increases much more rapidly with altitude than the mesotron intensity. So the cause of the penetrating showers could not be mesotrons. Indeed, it had to be either the primary protons themselves or the secondary nucleons which they generate in interactions with air nuclei. And a similar experiment done 10 years earlier by Rossi and De Benedetti at Padua had shown that the mesotrons do not cause the soft showers of electrons and photons. So the question became, what is the connection between the interactions of energetic nucleons and the soft component of electrons and photons? Well, in a separate approach to this problem, Herb Bridge began to build multiplate cloud chambers with which the tracks of charged particles are made visible as trails of droplets. He set up a chamber under a penetrating shower detector near Echo Lake on Mount Evans in a laboratory situated at 10,000 feet in pine woods that are frequented by deer and elk. But meanwhile, in 1947, particle physics began to get more complicated. Giuseppe Occhialini, who was Professor Rossi's first Italian student, was working at that time with Powell and Lattice in Bristol, England. Late one night, he recovered a nuclear emulsion from the trash where it had been discarded, apparently due to the hopeless overexposure to cosmic rays in a laboratory that had been high in the Alps. Examining the nearly opaque emulsion under a microscope, he discovered the track of a pi meson that stopped and decayed into a mu meson. And within a year, two more unstable particles, heavier than pions, the so-called V particles, were discovered in cloud chamber pictures by Rochester and Butler in Manchester. So Bridge and his associates joined the search for these new particles with their multiplate cloud chamber. The V particles were quickly confirmed, and in 1949, the first examples of K mesons were discovered in the form of what were called S particles. So here is a picture showing a typical S-particle event as the track of a particle which enters from above, stops in the sixth plate after scattering, and the increased ionization and the increased deflection show that it stops in this plate. And from the point of stopping, there emerges a penetrating particle that goes out the bottom of the chamber. Analysis of that scattering of the particle as it comes to rest shows that the S-particle mass lay between that of the proton and the pion, and that the mean life was longer than 10 to the minus 9 seconds. Those are properties of the K mesons, and this was the first example of the K meson that was published. And that's about the time that I joined the cosmic ray group as a new graduate student. I remember the all-night labors of Martin Annis as he scanned the films, and Stan Olbert as he worked out the statistical theory of scattering and energy loss of stopped particles. Stan was a Pole and a veteran of the Warsaw Uprising. He came to MIT as a graduate student sponsored by an MIT fraternity. And somehow he'd managed to study theoretical physics after the release from a prisoner of war camp in Germany. And so he arrived at MIT well equipped to provide the theoretical support needed in the particle research. His 40-year-old results on stopped particles are used even today in precise planning of treatments of retinal cancers with stopped protons at the Harvard cyclotron. And it was by a twist of fate that Professor Olbert himself was a recent and much honored patient at that facility. Now, Bridge and his associates continued their search in cloud chamber photographs for clues to the origin of the soft electron photon showers. They found what they were looking for in pictures that show a neutral link between a nuclear interaction and an electron shower. Now, in 1947, Robert Oppenheimer had suggested on theoretical grounds that the intermediary in electron showers might be an ultra-short-lived neutral pion that decays into a pair of photons. John Tinlow and Bernard Gregory used a cloud chamber with brass plates that would allow a photon to escape from the region of its creation in one plate and then materialize in another plate to form an electron-positron pair, leaving a visible gap or a neutral link between the interaction and the start of the electron shower. Now, examples of such neutral links can be seen in this quite remarkable cloud chamber picture. Here, a particle enters center stage from above. It passes through 6 plates and stops in this plate, as one can see by the increasing ionization and increasing deflection. 2 small electron showers emerge from the 7th and the 8th plate, respectively, and their directions diverge directly from this point of interaction in this brass plate. And their total energy is more than 300 million electron volts. There are no tracks linking the 2 downward showers to that point of interaction, and so the physical links therefore must be high-energy photons that carry no charge and therefore leave no track but do materialize into electron pairs. Gregory, Tinlow, and Rossi had found numerous examples of such neutral links by 1949 when they published their conclusion that pairs of energetic photons arise from the decay of neutral particles of intermediate mass, probably neutral pions, produced directly in high-energy interactions. So the mystery of the origin of soft component was solved by the verification of the Oppenheimer idea. And in the following year, experiments at the Berkeley synchrotron provided the detailed evidence of threshold production and coincidence detection of the decayed photons that confirmed the existence of the neutral pion. But this picture is especially remarkable because it contains the first evidence for annihilation of a heavy antiparticle. Looking more carefully at this track, where one sees that the deflections are increasing and that the ionization is particularly heavy, meaning that it's going slowly here, as I said before, proves that the particle stopped in this plate. Well, since it came to rest, it obviously did not have any kinetic energy to give to those electron showers that pass downward and to the left. But more spectacular is the energetic electron shower that emerges from the 6th plate and travels upward and to the right. Its energy alone was estimated at 1,170 million electron volts, and thus the total energy emerging from that stop point exceeded 1.4 GeV, more than the rest energy of a single photon. In their 1954 publication, the authors concluded that the event is an annihilation of a heavy antiparticle, either an antiproton or an antihyperon, an annihilation with a nucleon in the brass. And within a year, Chamberlain and Segre had identified antiprotons among the products of high-energy interactions at the Berkeley Bevatron. One final bit of particle physics was extracted from cosmic rays in 1957 before we abandoned them for the greener fields of space astronomy. Juan Herschel, who was visiting from Bolivia, and I, following a suggestion of Bob Williams, actually, based on the recent discoveries of parity violation and beta decay, we measured the polarization of cosmic ray muons in what is truly a tabletop experiment, perhaps the last one of its kind in cosmic, or nearly one of the last one of its kind in cosmic rays, that we set up in a lab in Building 6. Hale-Brott then extended the experiment in a greatly enlarged version carried out in an old limestone mine near Poughkeepsie, where they cultivate mushrooms. His measurements of muon polarization as a function of depth underground cast light on the production of pions and kaons in nuclear interactions of cosmic rays in the energy range from 10 to 100 GeV. But the complexity and the ambiguity of the analysis that was required to extract something of value was just another symptom of the end of cosmic rays as a useful source in particle physics. But now I want to go back to 1946 and the second of the Rossi research themes. Bob Williams had set out to determine the energy spectrum of primary particles by measuring the size distribution of extensive air showers. He built an array of pulse ion chambers like those Rossi had used in the Trinity experiment, and from the pattern of pulse amplitudes recorded when the array was struck by an extensive air shower, Williams could locate the core of the shower. He could then compute the total number of particles, and from that he could estimate the energy of the primary particle. In 1947, Williams published his results on the detection of showers of up to 100 million particles initiated by primaries with energies up to 10 to the 17th electron volts. And that was an astonishing extension of the primary spectrum and a challenge to theories about the origin and propagation of cosmic rays in the galaxy. Now, in the summer of 1952, Peter Bassi came as a visitor from Padua Institute that Rossi had started before the war, and I was just finishing my thesis. Professor Rossi suggested to us that we explore the possibility of determining the arrival directions of air showers by timing the arrival of the particles over an array of timing detectors. New liquid scintillators made it possible to build cheap, large, fast proportional counters, and we took Rossi's suggestion to heart and soon had a linear array of 3 liquid scintillation detectors set up on the roof of Building 6. Our results demonstrated that showers do, in fact, arrive as flat pancakes of particles about a meter thick, moving with the speed of light, just right to allow a determination of the arrival directions by a simple geometrical analysis of the differences in the arrival times. Several of us then began a program of air shower experiments to determine the energy spectrum and celestial arrival directions of primaries up to the highest energy that nature could generate. We felt there must be a high energy cutoff somewhere, perhaps near 10 to the 18th electron volts, where the magnetic confinement of the galaxy should spring a leak, or perhaps at 10 to the 19th, where protons are degraded by interactions with starlight. Surely there would be a telltale anisotropy at a sufficiently high energy that the radius of curvature of the primary particles in the weak magnetic field of the galaxy is comparable to the thickness of the galactic disk. So we built an array of 11 large scintillation counters filled with flammable toluene, set it out in the dry forest of the Agassiz Station of the Harvard College Observatory. And as Fred mentioned, we did overcome many problems, including rabbits chewing on the high voltage cables, and a little problem with fire in a detector struck by lightning. Well, the observatory, in fact, did not burn down. The scintillator was replaced with discs of homemade plastic scintillator, and the powers that be allowed us to proceed. Signals were displayed on a bank of oscilloscopes whenever several of the detectors were struck by an air shower. We photographed those oscilloscopes, transferred the particle density and arrival time data to punched tape, and analyzed it on the newly liberated Whirlwind computer. And we measured the primary spectrum up to 10 to the 18th electron volts. Here one sees the largest shower that was detected at Agassiz. It lit up all of the detectors in this array, which was nearly half a kilometer in diameter. And after analysis on the computer, we could fit a lateral distribution curve to the particle densities and derive from that the size of the shower and infer the energy of the primary particle, which was in excess of 10 to the 18th electron volts, a good fraction of 1 joule. But there was no trace of anisotropy and no trace of a cutoff in the energy spectrum. I set up a small air shower array in the south of India. Fruitless search for anisotropy in the southern hemisphere where the center of the galaxy is visible. We sent the entire Agassiz experiment with the cooperation of Ismael Escobar to the Altiplano in Bolivia to improve the statistical accuracy of the search in the southern hemisphere. Still no anisotropy. And finally, John Lindsley and Livio Scarsi carried the air shower enterprise another giant step forward with a huge array on the Volcano Ranch near Albuquerque. Here you see the volcano array, which was finally 3 kilometers in diameter, dwarfing the previous arrays. In their measurements, their spectrum reached 10 to the 20th electron volts, and where this is displayed here, where I've multiplied the intensity by the cube of the energy to flatten the steep spectrum out, and one sees that the data extend clear to 10 to the 20th electron volts. And just think, 10 to the 20th electron volts is 6 joules. That's the energy required to raise a 1 pound weight 4 feet. And that's a truly astonishing amount of kinetic energy to be carried by a single particle. And the mystery still remains. Where do they come from? As air shower research approached a point of diminishing returns and accelerators replaced cosmic rays as sources for high-energy particle physics, 2 new lines of research opened up that have occupied the cosmic ray group ever since: high-energy photon astronomy and interplanetary plasma physics. Sputnik flew in October of '57, and you could hear its beep-beep on the shortwave radio as it passed over Cambridge. In the ensuing panic, Rossi was asked to chair a committee of the National Academy that met in the summer of 1958 to examine the possibilities for space science on satellites. He found little interest anywhere in the possibilities of cosmic X-rays or interplanetary plasma, so he decided to initiate action himself. The Cosmic Ray Group was already at work on a satellite gamma-ray astronomy project that had been initiated in the spring of 1958 by Bill Kraushaar. So Rossi brought his ideas about X-ray astronomy to his former student, Martin Annis, who had just started a research company in Cambridge called American Science and Engineering. Martin decided to commit a portion of the company's meager resources to a paper study and to a preparation of proposals to NASA and to the Air Force. That effort, led by Riccardo Giacconi, succeeded with the discovery of the first X-ray star by a rocket experiment in 1962 that was, in fact, sponsored by the U.S. Air Force. And soon after that, several of us started work in X-ray astronomy at MIT, but that's another long and complex story that I won't attempt to tell. Now, during that summer of 1958, Rossi discussed his idea about space plasmas with Herb Bridge. Here you see them examining a test setup in the laboratory where they were exploring the possibilities of measuring plasmas in space. Now, in 1957, Eugene Parker at Chicago had published his theory of an expanding solar corona that blows past Earth as a supersonic wind of ionized hydrogen. There were observations of multiple comet tails that had been interpreted as an effect of a supersonic wind. So it was clearly a matter of great interest to test these ideas by direct measurements. Bridge and Rossi immediately started development of a device that could be carried on a deep space mission to measure the energy spectrum and flow direction of tenuous plasma. Here you see, in this picture, you see them examining one of those test setups. And Rossi succeeded in securing a place on Explorer 10 for the first MIT LNS plasma probe. Explorer 10 was NASA's first attempt to send a spacecraft to a large distance from the Earth. Now, of course, by that time, the Soviets had sent a spacecraft to the vicinity of the Moon. The Soviets had carried a sensor that did, in fact, detect plasma, but gave no information about its flow direction and little about its density and energy. And I was at the Cape Canaveral in March of 1961 waiting for the upcoming launch of the MIT gamma ray experiment, when the preceding experiment, Explorer 10, roared into space on its elongated orbit. I remember the excitement in the ground station when the first signals of a space plasma came through, as the detector on the rotating satellite repeatedly passed the direction of the sun. Here you see the picture of the plasma probe, which carries of the Explorer 10 satellite, which carries the MIT LNS plasma probe, designed to capture and analyze the stream of plasma that might be encountered. Analysis showed that over the course of several hours, on its outward journey, the plasma probe had detected alternating conditions of no plasma and of a supersonic plasma blowing away from the sun. The satellite rotated, and as it carried the plasma probe past the direction of the sun, which is indicated by these vertical lines, a signal of a supersonic plasma flow was received. And by good luck, that trajectory happened to be along the wavy boundary between the region of space dominated by the Earth's magnetic field and a region of steady flow of the solar wind that's now known as the magnetosheath. Explorer 10 had made what turned out to be the first measurements of the solar wind that and indeed confirmed the Parker theory, and it had penetrated the boundary of the Earth's magnetosphere. Several more plasma probe experiments were developed in LNS before the work was moved to the Center for Space Research, where it flourishes today. MIT plasma probes of ever greater sophistication have explored the magnetospheres of all the planets out to Neptune. Solar wind measurements are still received from Voyager 1 and 2, which are now on their way out of the solar system at velocities of more than 20,000 miles per hour. Sometime early in the next century, their trajectories will pierce the boundary of the heliosphere and provide the first direct measurements of the fields and particles in the pristine interstellar medium, a kind of scientific gift from this generation of space scientists to the next. The Rossi era in the Laboratory for Nuclear Science and later in the Center for Space Research has been a truly wonderful 46-year journey of exploration at the frontiers of particle physics and space science. I know I speak for all who have shared it with Bruno, whom I'm delighted to see here today. And for all of those people, I want to say to him, thanks for bringing us along. Thank you.